Hello and welcome to the directions video for Lab 10 from Astronomy 20. And this lab is all about planetary orbits and Kepler's laws. This is a lab where we get to explore the physics of orbits, which is all about the centripetal force taking the place of the gravitational force. So we have a seeming balance of forces, but really more of an allocation of forces. Think of that centripetal force as eating up all the gravitational force. So you have yourself a perfectly circular orbit, potentially, or you might have an elliptical orbit with some other forces that aren't exactly radial, which would be your tangential forces. But of course, I'm getting ahead of myself. So let's take a look at part one and get right into it. So this lab mentions some objectives, so I'll let you read those on your own. And most importantly, it mentions a simulator that you're going to find at fet.colorado.edu. So this is one of those FET simulators, which are well used in the physical sciences. Now, I've already opened it and was fiddling around with it. So let's go ahead and actually click on this link. And it'll take us over here. All right, so you can see that this is what it should look like when it opens up. Now you're able to run this in the browser. This is a modern simulator. And when we go ahead and open it up, we are good to go. Okay, now you can see that there's two choices here. We have model and to scale, and the lab is not as, I guess, obvious as I thought it would be, because it says click the play arrow, but then it says choose to scale. Well, I guess the play arrow is on the previous page. I would expect it to be here based on that wording. That particular part I did not write myself. Okay, so there's quite a bit that I did write and change, but then there's little things like that I didn't catch. In fact, there's another pretty significant point of confusion that I'm going to call attention to in just a minute. But this is the part of the simulation we want to use. So we're going to go ahead and click on that once to select it and a second time to start it. And we see by default, we have a planet and a star. Now, when they're to scale like this, that means that they're just tiny little dots because space is mostly just vast emptiness. Yet now, especially between stars, then it's unbelievable vast emptiness. But even in a solar system itself, the proportional size between planets and their distance is tiny, okay? A point of interest, the sun is 99% of the entire matter in the solar system. So everything else, including the giant planets like Jupiter and Saturn, make up 1% of the remaining matter. And that even includes the asteroid belts and the comets on the outer edge of the solar system. All of that, just a tiny, tiny bit of little specks that, in our case, life has taken hold on. Now, we're told to start a few selections here. We want to have the velocity grid, which we're going to put right here. All right. We want to have the velocity vector, I believe, as well. Make sure that, yeah, so the velocity, that's a particular selection. Okay, that's the one right there. I call it a vector because that's the name for an arrow that has both magnitude and direction. The mathematical name for it is vector. All right, and then we also have the measuring tape option, which we won't use right away, but it's pretty cool. That can show us the distance between things. For example, if we want to have the distance between our star, which in this case it's going to represent the sun, then and our planet. Here, let me do this correctly. Here, I'll put the X right there, kind of almost like the pivot, and then I'm going to line it up so you have center to center here. And we're going to have, although you can see that the circle around the star is not its actual size. The star is a tiny little dot inside of it. Oh, I see why. Because the V here is that that's the velocity. That's like actually the way that the program denotes velocity. But since the star does not have any velocity, it's the rest point in our reference frame. It's just that circle with the V, okay? But the star is a little dot in the middle of it. But anyway, I was talking about the distance here. You can see the distance is 147 million kilometers. That's known as an astronomical unit, right? That's a measurement of astronomical distances, right? A very common one. Essentially, that's the average distance from, that the Earth is from the sun, because our orbit is fairly circular, but not perfectly circular, okay? Now, the simulation we're going to use is by default the sun and Earth, which is described in one of the next steps. All right, so we're told to go ahead and use the sun and Earth, right? And then the Earth should be 2 grid boxes by default. Indeed, it is. So you can see each grid box represents 1/2 of an AU. That's kind of a cool conversion, right? All right, then we're going to click the big blue play button, right? and then we're going to change different speeds of playing it, and then we're going to click the gray reset button. Okay, so this time we're actually going to click it. More on that in just a minute. I hinted at it before. This is the only reset button you will ever use. Well, yeah, but we actually won't use it as much as the lab says to. Now I'm going to try to update the lab, and I'll say where I want to, but for now I'm just going to point out what to do in the video. And it's something you could work around certainly, but it is confusing the way it's described. Okay, but for now nothing is terribly confusing. We can go ahead and hit the play button. We can see our planet carrying out what should be a nice circular orbit. A good way to look for that is to see if it crosses on these next intersections between the grid here, right? Because if it's going to get exactly right, you can see actually it's not, right? It's slightly further over here, and that's indicative of the fact that this is modeling the orbit of Earth, and it's not a perfect circle. Right, so it's going to get back and pass exactly through that point because it will return to where it started. It's all the energy is conserved here. We're not losing any significant amount of energy in one orbit, not at all, right? The planet's been orbiting for billions of years. We can slow things down, right? It becomes incredibly slow. That's more important if you're doing a really close orbit, and of course we can speed it up. Right, so you can think of a kind of our scale here, right? And it keeps reading. It doesn't reset after 1 year. So now that we've completed 2 complete years, we have over 700 days, right? Earth days at least. I don't know if those are sidereal days or solar days. It wouldn't matter, to some reasonable rounding. Okay, so let's go ahead and stop that. Now, if we do set the reset button, it'll bring the Earth right back to the basic conditions for the Earth-Sun system, which means it will always bring the Earth back to 2 grid boxes away from the quote-unquote star, right, which in this case represents the sun. Now, that's the problem, is at later points, we're not actually going to want to bring the Earth back to 2 grid boxes, its actual distance, right? It's realistic distance. Instead, we want to have some hypothetical alternate distance, okay? So if you take a look, one of the first things we're going to do, I'll mention number 1 in just a minute, which is the calculation, one of the few, okay? We're going to want to actually move the Earth to 1 box, okay? And then we're not going to change the length of the velocity vector at all, and we're going to predict what's going to happen, okay? So I'm going to go ahead and move it over there. Not the measuring tape, but the actual planet. And if you click on it the same way that you click on the measuring tape, it's just a drag and drop. All right. So we're going to drag our planet right over here. Okay. Now, what do you think is going to happen? Now, this is important because if you're not making a prediction now before you see what's actually going to happen, you're going to miss out on that part of the lab. So please make a prediction, all right, before you watch this part of the video. Okay. All right, so I assume that you have made your prediction. So now let's take a look at what's going to happen without changing the velocity of our modeled Earth, but drastically changing its orbital radius, cutting it in half. Okay, let's play. Whoa, what was that? Okay, what is going on? Well, I was talking about elliptical orbits. That's an elliptical orbit. See how the velocity vector gets longer? That is indicative of conservation of energy. We have gravitational potential energy getting converted to kinetic energy. So the planet is speeding up, okay? Some planets and comets and such have very elliptical orbits like this, even more so. All right, okay. Now let's think about how we would want to reset things, okay? So I'm gonna go ahead and hit pause. Now, if you look at the next part of the lab, it says click the reset, okay? And then stretch or shrink the velocity vector so that when you hit play, the orbit is circular. Well, what the lab is referring to here is the orbit at 1 grid box. We already know it's going to be circular, or darn close to circular at 2 grid boxes, and we want to get that close to circular, but at 1 grid box, okay? Now, right? And then it says don't reset after each new velocity, but instead use the rewind button. But it actually should have never told us to hit reset, because if we hit reset right now, it's just going to bring it back to 2, okay? So on all the future, the future runs, right? Certainly hit rewind as described there, but also hit rewind at this step here, right? Don't bother to reset, okay? All right, and then by the way, what do you think would happen, right? All sorts of interesting things, but I don't want to give too much away, so I won't show you, but you can imagine what would the orbit look like if the velocity was really, really small, right? What if it was just right? Well, supposedly we can get it to be a circle. But let's take a look back at question 1, because this is the calculation that asks us to calculate the velocity of a stable circular orbit, in this case for Earth. Okay, so this equation is a very common equation for satellites, both natural and man-made. So if someone wanted to put up a communication satellite or a weather satellite or the International Space Station, this could tell them the velocity of that orbiting man-made object based on its distance from the center of Earth. So R here would represent the distance from the center of Earth, okay? And right, that's perfect because it is a center to center distance, which is how r is always measured. In that case, it would be the center of the planet to the center of the satellite or the space station. Now, between planets, we can use the same idea. We also can apply very equally well to, say, finding the velocity of the moon relative to Earth, right? So if I wanted to find the orbital velocity of the moon, and to actually have a analytical solution, right, to plug in the numbers and get an estimate of how fast it should be, I'd plug in the value right here, which is called the universal constant of gravity, right? Now, that value right there, this also for short just called the gravitational constant, is 6.67 times 10 to the negative 11, right? So it's a very small number, right? Almost a trillionth of one. The units are force area over square mass, or newtons square meters over square kilograms, okay? So those are the units that actually just make the equation work out. The equation being Newton's law of universal gravitation. This is what's called a fitting constant. It's determined experimentally, right? There's no law in physics that tells us it has to be this number. This is just the number that scientists have discovered, right? We don't know where the number comes from. It just is apparently the way the universe is made. Okay. Now, m is a value that is discovered, right? It's a particular value that applies to one particular object. In this case, the mass of the sun, right? Because if I want to figure out the orbital velocity of Earth, and that's what we're solving for here, relative to the sun, then the only mass that I care about is the mass of the body that's being orbited, which is always the larger one, right? Now, I guess you can have two equally sized bodies kind of orbiting each other. That's like a binary star system. They can orbit like an empty space, which is the center of mass of the two-body system. But that's neither here nor there. What we care about is cases where you have a large thing being orbited by something that's much smaller. Now, Earth is about 1/1,000,000th the volume of the sun. So yeah, indeed, much smaller, right? Now, the thing is that the reason it cancels out is actually because of Newton's second law. And I'm referring to the mass of the body that's orbiting, in this case, the mass of the Earth. So it just doesn't show up in the calculation. The same if I was to solve for the mass of a satellite, well, the orbital velocity of that satellite would be completely independent of the mass of that satellite, right? Very, very interesting idea here, okay? And then r is just the distance of it's the orbital radius, okay? So in our case, then it's going to be, one astronomical unit. Okay. Now it says here that we can find out how far it is by noting that each grid box has a length of 74 million meters, actually 74 billion meters, or 74 million kilometers. Okay. You can see here the measuring tape is in kilometers. That's the way we typically refer to that AU I mentioned. We say it's about 150 million kilometers. Well, that's the same as saying it's 150 billion meters, because there's 1,000 meters in every kilometer. Okay. So now, if we actually do reset it right here for the sake of discussing the calculation here, since we have gone back to problem number one, well, sure, you can count that each grid box is that much and then realize there's two grid boxes away and double it, or you can just, get your measurement right here in kilometers and make sure to convert it to meters. This equation will not work if it's in meters, okay? So let's then go ahead and find out, what would be the orbiting velocity, but let's not use these numbers because I don't want to give away the solution here. So instead, we're going to go over to Desmos and consider some completely other orbital case, right? Let's consider some m, something that's more like they say the mass of Jupiter, maybe. So how about 3.33 times 10 to the 27? It might be a little too big. Earth is 10 to the 24. Sun is 10 to the 30, as you can see here, right? That's the number of zeros, right? So yeah, sure, 10 to the 27, okay? So that's our thing that's being orbited. I'm considering like a moon orbiting a gas giant, right? And let's go ahead and then have an orbital radius of, how about, you can have one is almost as big as an astronomical unit, but let's go with 1 billion kilometers. Okay, so 1.00, well, that's gonna be too round of a number. 1.45 billion kilometers. So 1.45 times 10 to the 9 meters. Okay, right? So I said kilometers a second ago, meters. Okay, now since that's billion meters, that would be million kilometers. So this would be 1.45 million kilometers. Okay, so about 100th of an astronomical unit. All right. So then let's see then what the velocity of this orbiting body would be based on those parameters. I'm going to go ahead and define g as well. Now you don't have to use Desmos, just it is awfully convenient. So 6.67 times 10 to the negative 11. All right. And so then let's go ahead and solve for velocity based on those numbers. Okay. So I have our g right in front, and then I'm going to have my m and divided by r. Okay. So you can see that's how everything shows up in the equation. And we can see then that the stable orbital velocity of a circular orbit at this distance from this massive of a planet or whatever would be 12,000 meters per second. Okay, so 12,376, but that's too many significant figures. So really we could just round to two significant figures here based on our numbers. I guess I used three in all of our values. So how about 12.4, okay? In kilometers, right? Because that's, this is 1,000, right? Or you can even say 1.24 times 10 to the 4 meters per second. That'd be a way to express the velocity in scientific notation, because the 4 would come from the fact that there are 4 places after where you put the decimal mark in proper scientific notation, okay? Alternatively, because a lot of these velocities end up being on the scale of meters, a lot of times you'll hear them, kilometers, you'll hear them described as kilometers per second. So in this case, it'd be 12.4 kilometers per second. That would be the orbital velocity, okay? That's actually pretty fast. It is, of course, a massive body. The more massive the body is being orbited relatively close, those are going to be faster orbital speeds. A lot of man-made satellites that orbit around Earth are orbiting around at about 6 or 5 kilometers per second, okay, to put things into perspective. Now, Earth is going to be a bigger number than that, right, because the mass of the sun is going to bring that number up if you think of the calculation. Now, you're actually going to make a similar calculation, moving on, in number 5, because in number 5, you're actually going to then say, okay, we got the one grid box now. You were, through trial and error, trying to figure out how long to make your velocity vector. Well, what's the actual number, right? Well, you can figure it out, right? So that you can find, and that now there's no way to exactly confirm that with the program, right? The program's not going to read out the velocity, but you'll know then that length vector actually represents that many kilometers per second, say, okay? All right, so then moving right on, we're going to move the Earth to 3 grid boxes. This is the first time we're moving it to 3. It actually would make sense. The last calculation was thinking about 1 to actually probably hit the reset button, because it doesn't really matter, right? And then move this measuring tape out of the way and move it all the way to 3. Same sort of thing. You're going to leave the velocity vector unchanged and make a prediction about what's going to happen. Then you're going to hit the play button. Here, do not hit reset, okay, because you want to keep it at 3. It'd be a pain in the butt to have to move it one more time. Not that inconvenient, but certainly then after each trial, don't reset it, right? Just let it continue, right? And then continue in the sense of rewinding it, right? So let me go ahead and kind of show you, because we already got to see some stuff messing around with the 1. So if I don't want to give anything away on the 3, but if we'll go back to the 1. And we have it here, right? Now, one actually cool option that you can do that wasn't mentioned as one of the default things to turn on, at least I'm pretty sure it wasn't. We can scroll back up, and that's the path option. Let me see if that was. So you have grid, diagram. No, but I could see not recommending it all the time, but I'm going to show it here because it is actually pretty cool. If we turn on the path and then we let it run, right? So let's have it go through its orbit. Okay, so it's going to be an elliptical orbit. What's cool is you can have it, if you're quick about it, pause it kind of right there, then change its velocity. Okay, so we'll just bring it down a bit, and then keep it going, right? So what I've done here, now I nearly made the planet crash into the star there, right, our sun, right, is now I can really kind of see, right, that I got less circular, right? So clearly, I went in the wrong direction. So if I make it longer, right, I can see then, oh, okay, now I'm getting something better, right? It's still certainly not perfect, but okay. And so what if I make it even longer, okay? So it's kind of cool about that option is that now when you should try to do it, say I wasn't that careful and I didn't do it right when I kind of got back to that point, but I can get something then that starts to get more like a circular orbit, right? And you get to see that progression as you go. Now you don't have to do it that way, but importantly, don't hit reset, right? Because then you'll be at a different grid point. Okay, so then we're going to change another parameter, right? So this time it would make sense to hit reset because we do want to get the sun back, the Earth back to its default position. Because here the only thing we're going to change is the solar masses, all right? So we're going to take it all the way from one solar mass, which is our sun's mass, of course, right? There's multiples of our sun's mass, which we now know is, some 10 to the 3, 10 to the 30, excuse me, kilograms, right? So if we scroll back up, remember, this is the actual, right, mass of the sun in kilograms. But a lot of times we just mention masses, lots of masses of stars, is just multiples of the mass of the sun. They range all the way up to hundreds of times more mass of the sun, or a lot of them are actually similar, slightly less, like about half the mass of the sun is one of the most likely sizes. Okay, but here we're going to do 2, right? Such as big as the simulator lets us go, and then we're going to go ahead and run the simulator, hit play, and make a prediction. I'm not going to give it away this time. Right? I'm going to stick to just giving away that 1 as much as I can. Then it says to hit reset. I would again caution against doing that, okay? Because if you do hit reset, right, it's going to bring it back to one sun, right? Which is not what you want. Instead, hit rewind, okay? So right here, this should be rewind, not reset on question 11, okay? Then we're going to use that equation again, equation 1, right? So we're just using the same equation now. This is the third time to make a numerical prediction about what the velocity should be with this more massive, a source of gravity at the center of the orbit, okay? So how do you think that's going to affect the numbers, right? Then you're going to go over to the smallest mass that the simulator allows, which is 1/2 the mass of the sun. So going, those are the extremes, right? To half to double, right? Same sort of thing. Leave nothing changed about the Earth's position, okay? The default Earth position. Go ahead and click play. See if your prediction is correct. And by the way, on 12, it does make sense to reset because you are going to be changing everything from the defaults. All right. After that, then you're going to, on 14, don't hit reset, and instead hit rewind. So you can keep the mass of the sun at 0.5 solar masses. I guess it's not the sun anymore, but our new replacement star. Okay. Then you're going to do the calculation yet again, the fourth time with equation 1. Okay. Which is good. You're getting practice and repetition. Then you actually are going to reset it. Okay. In this case, you're going to change the mass of the Earth. Okay. Just the mass of the Earth. Okay, then you're going to go ahead and play it, right? Make a prediction. Was your prediction correct? All right, then change the mass of the Earth again. Okay, make a prediction. Mention if your prediction was correct. Okay, then talk about which of the tested parameters actually affected the speed of the orbiting object. Did they all affect it? Did only some of them affect it? Okay, so that's it for part 1, which is, all about this idea of looking at orbits. Okay, so it's very focused on really Newton's laws. Okay, that's because that equation that comes directly from Newton's law of universal gravitation and Newton's second law. And by that equation, I mean equation 1, the only one we've seen so far. Okay, but in part 2, we're actually going to go and take a look at a different simulator. Okay, so let's go ahead and follow this link. All right, so this simulator is not put out by the University of Colorado, but instead Nebraska. This is one of the astronomy department simulators, which has the acronym of NAP, N-A-A-P. So let's go ahead and click on that and navigate over to it. This one also should run in your browser. It's a nice modern simulator, works quite well. Okay, now there's some directions here about how to set things up. All right, so if we're not already running it, launch it. Well, we just did that. Now you can also download these. There's native app versions that you can run on your computer without, say, internet access or not on the web, which is not the case with PhET, okay? Not without knowing a lot about how to get some of their legacy versions that did used to run kind of like in JavaScript, but good luck finding a program that actually runs them. But anyway, so here we have, we're going to click on Kepler's first law tab, all right? Then we're going to enable all 5 checkboxes in the central lower region of the simulator, okay? We're going to explore them, understand what each of them means. Then we're going to explore moving the white dot around by dragging it with our mouse, okay? So let's go ahead and take actually a look at some of this. Okay, so we're in the first law. I'm going to click all 5 boxes, all right? So this is showing a bunch of information about ellipses because Kepler's first law, to give you some background here, states that all orbits are elliptical, okay? All stable orbits are elliptical, or closed stable orbits are elliptical. There's also trajectories, which can be parabolic or hyperbolic, but every orbit that can, actually comes back around on itself is elliptical. Now, what about circular orbits? Well, a circle is a subcategory of an ellipse. It's just an ellipse with 0 eccentricity, okay? Now, we can see that ellipses have some defining characteristics. They have 2 foci. The body that's being orbited is always located at one of the 2 foci, and the other is always empty. Okay, they have a center, which is where the semi-minor axis and the semi-major axis meet. Why is it called semi? Well, if the major axis is all the way across, okay, kind of like a diameter, right? And the same way that a radius is half a diameter, a semi-minor axis is half a minor axis, just like a semi-major axis is half a major axis. They're called minor and major for obvious reasons because the major axis is always the longer of the 2. The minor axis is always the shorter of the 2, okay? So we're showing all that information here. All right. And so then it says, say, turn on the show grid option as well. Okay, we'll put that right here. Okay. And I'm going to leave off the show solar system objects for now. All right, so change the size of the orbit with the semi-major axis slider. Okay, so we can do this right here, see? And it will auto scale for us. So you get, so it's like, first you can't see it. And so it's kind of interesting because it kind of looks like it doesn't really change. You're like, oh, it just looks like the same, right? But remember that, you are getting an idea of the different sizes because we have a map here, right? So we know here that, that's 1 AU, whereas you make things really small, we know that that is now, a tenth of that. That's 0.1 AU. Now remember, an AU is about 150 million kilometers, right? The average distance of Earth as it orbits around the sun. Okay, so the other thing that we can adjust here is the eccentricity. That's why I mentioned about perfect circles and not, right? So if I make the eccentricity all the way go down to 0, I have a perfect circle. So what's happened now is my two foci have actually kind of overlapped on top of each other, and they're not actually two separate points anymore. They are just the center, okay? So there's no such thing as two separate foci, right? The empty foci is also the filled foci, which is the exact location of the sun, right? Or the body is being orbited. I can go all the way to the other extreme and turn up the eccentricity as high as the simulator will allow us to go, which is 0.7. Now that is not an actual physical limit. There are eccentricities higher than that, both mathematically and in the real world in terms of orbiting bodies. But you can see that it gets quite elongated, right? So the more elongated, the greater the distance between the foci in this case, right? You can see that they get close to the sides themselves, right? Eventually, they essentially start to touch the sides. And, so that means that what you have mostly is just distance between the foci, one empty, one populated, and that defines our really stretched out ellipse, okay? What else can we change here? All right. Oh yeah, the maximum value is not real, right? Just as much as the simulator will go, as I just mentioned. It says test out animating the simulated planet, select an appropriate animation rate. The planetary presets set the simulated planet's parameters to those like our solar systems, okay? All right, as well as one dwarf planet as an option, right? So we can actually, turn on some values here, right? We can set parameters, right? So we can choose from everything, the 8 planets and what used to be considered a planet, Pluto, now just one of a few dwarf planets. Other dwarf planets of note would be like Ceres, for example, or Makemake. But Pluto is the most well-known, although Ceres is up and coming as a well-known dwarf planet. It's actually closer to home. It's in the asteroid belt, although it's not as large as Pluto. But it is a proper dwarf planet in the sense of being spherical, and the only one in the asteroid belt. By the way, if we were to set our preset to say Jupiter, you will notice that and I say okay, the values will set to that. We'll zoom out so we can actually see it. Now, what's cool now is we're actually seeing the orbit of Jupiter, which you can see is pretty darn low on the eccentricity, so almost a perfect circle, right? Now, you can tell that the empty focus and the focus with the star are not exactly at the same place, right? And you can make out the center there, right? But you also can see all the interior planet orbits, right? So you can see the orbits of Mars, Earth, Venus, and Mercury, all for the terrestrial planets. You can see there's a big gap between the terrestrial planets and the first of the Jovian planets, the gas giants, right? So Jupiter is the first of them and the biggest of them. And you can see significantly further out the next gas giant in order, right, from distance from the sun, which is the orbit of Saturn, or is the gas planet Saturn, okay? Less massive than Jupiter, certainly, are similar in size, just much less dense. So here we have two very well-known planets, and quite interesting that you can see how the gaps between planets really dramatically changes. Real defining characteristic of the solar system. We can zoom out more and look at Uranus, of course, all the way out to Neptune, and so on. Okay. All right. So, and then there are some questions here about the elliptical orbit. All right, all about the concepts of Kepler's first law. All right, including some concept questions that you just need to reason out based on kind of your information here. Okay. All right, change the eccentricity, continue on. Okay, so as you might guess, the very next step is to move on to Kepler's second law, right? So we're just kind of carrying right on. Now, if you get stuck on a lot of those questions, because many of them are very conceptually based, you can actually take a step back and go to the Planetary Orbits page and take a look at some of the background reading. All right, so there is some main content here, Kepler's laws of planetary motion, which has some simpler simulators and all kinds of background reading. Okay, so that's a great way to get some perspective on this. All right. This one gets more into Newton's role as well as universal gravitation, right? It might apply to the first part of the lab. Okay, so now the second of Kepler's laws, Kepler's second law, is all about this idea of conservation of, well, really angular momentum or energy, but it was originally described by Kepler as a conservation of an area swept out in the ellipse. And so that's the purpose of this, is to focus on this sort of historical perspective on what now we really know as a conservation of angular momentum and energy, okay? And what does it look like? Well, we can say start sweeping, right? And we can see that it sweeps out a fixed amount, right? So that amount was fixed at 1/16 of the overall size, okay? That's the area enclosed by the orbit, right? So if I was to adjust it to 1/2, well, it looks like 1/2, right? This is, and these are, they're all going to be these even numbers, a fifth, right? All integer fractions like this, okay? And it will tell you how long it takes to sweep that amount out, right? In this case, 0.167 years, okay? And we're simulating Mercury here, which actually is a good choice because Mercury is one of the most elliptical of the major orbits, okay? Although we can come up with, hypothetical more elliptical orbits. All right, there's a sound effect, which I wouldn't necessarily recommend. We can actually sweep continuously, which is kind of interesting. So if I start sweeping, it will just keep sweeping them out, right? So every one of those is 1/16, right? And so then once it's done, you can see that it will exactly have filled them in. Now, what's interesting is that last one will stay behind, making that sort of shaded color. So we can actually, we could erase all the sweeps, then start it again, and we won't have any of that overlap. And we're just going to have in this case, 6 equal area wedges, right? So like wedges of a very lopsided pizza, okay? All centered around the focus, right? So it's kind of interesting, not around the center, but the focus, okay? And this all has to do with the idea that as the planet gets closer to the star that is orbiting, in this case, Mercury getting closer to the sun, it speeds up because some of that gravitational potential energy is becoming kinetic energy. And that's causing it to speed up, which means that it's going to cover a greater distance, right? A greater portion, an arc length of the elliptical orbit in the same amount of time, right? Because every sweep has to take the same time. Okay, that's the idea. Same area, same time. That was Kepler's second law. Okay, so neat visualization here. Now, it goes on to talk about particular questions about how it relates to passing over parts of the ellipse, like the minor axis and so on. You can turn on, let's see, what other options? We can turn on the grid there, right? Kind of see the effect. That would help with seeing where it passes over the minor or major axis, right? Because we have vertical lines of reference. We also are going to manually control the eccentricity rather than selecting a planet to model. Then we're going to just continue to answer some questions. And then we're going to get right to the last part here, which is Kepler's third law. So you're not doing the Newtonian features, right? So we're calling it here at Kepler's third law. And let's go ahead and clear our optional features. All right. So what Kepler's third law is all about is a mathematical relationship between, really, I guess, proportionality between period and semi-major axis. So A, right, is a semi-major axis. Now, for a perfectly circular orbit with an eccentricity of 0, A equals R. It's the radius, okay? But for some other, non-zero eccentricity ellipse, A is the semi-major axis, okay? Now, P is the period of one complete orbit, right? It's always the same. That's the thing about stable orbits. Now, there's a little glitch here. I don't know if this would show up on a PC or maybe in a different browser. I haven't checked. But that 2 should actually be squared, right? So it's correct up here where as I'm mousing over. So you can see that it's P squared. So it's the period squared equals the semi-major axis cubed. And then so if you have a period of 1, okay, and you square it, that's going to equal a semi-major axis distance of 1 cubed, because 1 squared equals 1 cubed, okay? But the 2 should not be behind it, kind of half over the parentheses. It should be in front, because it's a squared value, okay? Now we can change it from 1 and 1, right? So we can actually drag here on, we drag over here, okay? And it will show up on the graph. Let's see. All right. Oh, what am I doing wrong here? So let's pause the animation. That's why, okay. So then I can adjust things. So I can then make my semi-major axis a different size. So you can see here now it's not 1 and 1, right? Instead it's 4.61 on the period, which we can see is the vertical value on the graph measured in Earth years, so all relative to Earth's orbit, and then 2.77 in semi-major axis measured in units of AU, so essentially Earth orbit, multiples of Earth's orbit. And that was the idea about Kepler's third law. Is it was a proportionality law. I say that because period squared, that's time squared, okay, years, but some millions of seconds. And then, of course, the semi-major axis is distance, so meters. Well, seconds don't equal meters, right? And every physical equation has to actually have the same units on both sides. So this is the proportionality, right? So it works if we have it in multiples of, all orbiting the same body, so multiples of Earth's orbit, orbital period and orbital radius. But it wouldn't work for another system, even the system of, say, the moons around Jupiter, the moons around Saturn. Okay, there you actually need Kepler's, universal law of gravitation and second law synthesized with Newton's universal gravitation law and second law of motion, right, which is F equals ma, by the way. And you take those laws from Newton, you synthesize them with this Kepler's third law, and you get Newtonian features, okay? But we'll leave that out for now. So you're going to adjust the simulator a little bit, control some of these different controls and including turning the eccentricity up to, does it let you turn it all the way up to 0.97? Let's see. No, 0.7, okay? So what is the period? Oh, well, there you go. See, this is a good one, 21, because you actually can't manually check this with the simulator. You have to use the equation, right? Because the simulator doesn't let you turn the eccentricity all the way up to 0.97, right? Highly elliptical, right? It's a comet, by the way. It comes around, every, hundreds or thousands of years, or sometimes hundreds of thousands of years. It's Halley's comet. I'm not sure about its exact period of motion. I have to look it up, but it has a semi-major axis of 17.8 AU, so quite long, right? It goes way out deep into the solar system. But point is that you can plug these in, right, and actually get the period. Okay, so you can calculate the period just based off of the semi-major axis. Now, to be fair, does the eccentricity affect this equation here? Do you see the value of eccentricity show up in this? Well, I'll let you think about it, okay? Oh, by the way, you can also change the graph from linear to logarithmic. So when you make the scales logarithmic, the curve looks like a line, because when you make the axes linear, then you actually see the curve. Okay, so it's kind of your choice how to do it. And then, of course, there's just a couple more questions. There's not too much here with Kepler's third law, kind of wrapping up the lab. As you can see, I'm also wrapping up the video. Well, I hope you have found this video helpful and gives you a solid foundation on how to work with both of these simulators from these excellent university programs. And I hope they just are fun and interesting and show you a lot about these topics of astronomy. Okay, bye for now.